Welcome guys, Max of the Accidental Engineer here. Today we are rejoined by Charles Martin, data science consultant with Calculation Consulting.
All right.
Great to see you.
Great to see you. Good to see you again. All right.
Welcome. One of the topics that you and I kind of touched on last time that I know is of tremendous interest to you is the distinction between science and engineering, and how engineering kind of focuses on making money for businesses, while science is a very time-intensive, resource-intensive discovery phase. And this has a lot of parallels to the type of work you do as a consultant. But one of the things that I wanted to ask you about was, how do consultants like yourself or scientists work around this funding problem, this financing problem? How do great innovations in science get funded so that they become common practice in engineering?
Well, look, I think you have to find the right clients.
Sure.
Right?
No,
you have to find, what is it that makes a client a good candidate for a data science project or a machine learning engagement.
What is that?
And if you go talk to like the Clouderos or the Databricks of the world, their job is to go in and build infrastructure. Set up Hadoop, set up Spark.
So data lakes.
Data swamps. They want you to. It's basically a consulting dream for them. You're going to go in and spend a year, 9 months, a year, 2 years getting this thing set up, and it's basically all building infrastructure. And that's what I mean by engineering. I mean, you need to do it, but it doesn't generate revenue for you. It's basically, you have very large companies who will afford to do this because they think they need to do it, and you talk about doing science, you're talking about trying to find ways to generate revenue fast. How do I solve a problem quickly? Mm-hmm. And how do I get it into production and start running experiments? So the key to being able to do science in industry is to be able to start generating revenue and as quickly as you can, and to begin running experiments in production as quickly as you can. So you can begin figuring out how to begin building and building revenue, building some stream that will support the activity. I mean, a good machine learning AI engagement should be self-funding. Mm-hmm. You should generate enough revenue within the first month or 2 months of the project that you can fund it for a whole year. Mm-hmm. That's what you're looking for. And the key to that, you have to select the right clients and the right targets so that you feel that you can get the right data and that you can start getting things working in production as quickly as possible. We had a client last year as a computational advertising client. They had worked on a year. They brought a mathematician in from Harvard. They worked on a year trying to get Hadoop running and to generate revenue. I said, this is just,
sucks.
Yeah. And it came to me. I said, I worked with the CTO who was a genius level coder. I mean, some of these guys are phenomenal. Willing to work, sleep 4 hours a night, can just code all the time. Mm. And within 2 weeks, we hacked together a machine learning solution in Ruby. Mm-hmm. In Ruby. Because they were Ruby guys. So we'll put you a Ruby solution together. And using, some command line tool. And within 2 weeks, we had revenue up by 10%. And within the end of the month, we had revenue up 35%.
So besides crazy, amazing results, finding customers that have latent data that is well-structured enough that you can come in and work with it, what is kind of the tool set that you come in with software-wise to do this analysis? Like you just described using Ruby, but shelling out to other open source software. Do you
well, sure. I mean, look, as I said, as science engineering, we use the same tools you guys do. We just do something different. Look, you have to look at what people are doing. Are they doing Java? Are they doing Ruby? Are they doing Python? Are they doing Scala? And you pick the tool that you have to pick something that can put into production quickly. I prefer using Python. Python is very easy to do. I can spool up a node on Amazon, and we can have experiments up. And you just basically start pulling data out of whatever data store you have, stuff it on S3, and you begin running, and you just begin running things in production immediately. It's very easy to set up.
In terms of the machine learning libraries, Python is kind of the glue between several tools.
So you have the main libraries are scikit-learn.
Sure.
That's your Python go-to. You've got now Keras, which is basically the Python interface to TensorFlow. Okay. I have some tools for doing things like causal inference.
Okay.
Variation. I'm looking at a new tool, variational autoencoders for causal inference, which are written in Edward, which is it's a Bayesian modeling system written in Python.
Okay.
So it's used for marketing science. How do you do Bayesian inference, a large scale Bayesian inference? Things like this. I saw there's in the old days we did everything on the command line, just using liblinear or Vopel-Rabbit. So those are very good tools.
Liblinear, Vopel-Rabbit. What are the licensing terms of those?
They're open source.
They're a great example of what was probably previously science research.
Let me give you an example. So
Sure.
there's many years ago there was a tool called SVM Lite out of Cornell. And SVM Lite, in fact, I used it when I was at eBay 10 years ago. We were looking at using this tool. And the problem was the tool wasn't open source for companies. So they didn't open source it. And so nobody used it. They stopped using it because we can't put this thing into production. We don't want to deal with it. We're going to pay you a licensing fee. I mean, some people, I understand that there were some companies, I knew guys at companies who were paying the licensing fee to do this. But why would you pay a licensing fee for this when you can just get liblinear for free? And it's totally open source.
Sure.
And I think when I was at, and companies don't want to pay they don't want to pay these licensing fees for tools.
Why not?
They don't want to spend them out. When I was at BlackRock, they wanted to stop paying licensing fees. We want to don't pay any licensing fees. We want to get rid of MATLAB and just use R. I go, okay, great, use R, or just get rid of SAS. Get rid of these things. Why would you pay? You don't want to. You just get locked into this vendor and you have to pay this licensing fee. And there's plenty of good open source stuff out there. In fact, even for my practice, we're looking at building a platform and just open sourcing it and giving it to people because it's not what we do. We're not there to sell you software. We're there to solve problems. And so if you need software, we'll just give it to you. Just take it, open source it. We can reuse it on other clients. You can extend it. It'll be fine. I think that's especially now with Google TensorFlow. Who would use anything else? I mean,
very well maintained, well financed, meaning they're paying the salaries of probably tens of employees full time at Google to maintain
Hundreds.
Wow.
Google's entire effort is all they talk about.
Yeah.
That's all Google and Facebook talk about now.
Facebook as well.
Well, they have Torch. They have Torch.
Okay.
And their Lua tool, which was built at the Courant Institute, the old Lua tool which is called Torch.
Okay.
But people stop using this now. I mean, Google has now put so much effort into this, and they've open sourced it, and moreover, they have libraries on top of it, like Edward and Keras, and I saw a new reinforcement learning library. I mean, they're phenomenal. They're phenomenal.
Is the future of financing science the megacorps like Google?
Well, science is pathologically sick. I mean, the university system is pathologically sick. They have some serious problems. I mean, I think Peter Thiel has really pointed out, what a bubble academics has become.
In terms of the tuition?
Yeah, I didn't pay anything to go to school. I appreciate it. I didn't pay anything, like a few $100. I mean, that was it. We had no debt.
The good old days.
Why would you take on debt to go to school? That's the whole point of a PhD. You get a great education, and they pay you. So I think that there's a huge problem in the academic that you start producing all of these people. They can't. How are they going to pay all this back?
There's an interesting recent news article about Google's funding of academics at universities, and I didn't read the details into it, but it sounded like Google was providing grants along the lines of NSF to researchers. And that brings up all kinds of.
They're also hiring researchers. I mean,
or
Uber hiring buy entire departments. I mean, why would you? It's a real problem. The problem with the academic world is that, the research is done by graduate students and postdocs.
They're cheap.
Yeah, but they're also not experienced. They're not experienced. The difference between having 20 years of experience in the field and having 1 year and taking a few classes.
Yeah.
And, nothing, that's not, we had these guys at Chicago, these great researchers, who could, they're productive into their 70s. And they're still doing amazing things. And now it becomes the entire, with the fall of the Cold War, as it was explained to me, the fall of the Cold War, the funding, the whole entire situation changed. And so you go into academics and your entire time is spent raising money.
Yeah.
You don't actually do any work.
Well,
how's that any different from what I do?
Yeah. Well, you're telling me some pretty compelling stuff about how much science originated from just the pursuit of the nuclear bomb and the pursuit of the end of World War II. You mentioned a couple scientists' names, so I'm blanking on.
Well, I mean, like Enrico Fermi.
Sure.
So, yeah. A lot of science, for example.
Well, a lot of science gets funded in the pursuit of ending wars or winning wars.
Well, I think even that people don't really understand. They don't know the history of how a lot of modern 20th century science came. The Germans funded the development of quantum mechanics because they were trying to corner the market on light bulbs.
Yeah.
and they wanted, you ask what is, think about guys who know physics, black body radiation, it's a light bulb. What did Einstein get his Nobel Prize for?
Relativity.
And it wasn't general relativity. It was it was a photoelectric effect. Light bulbs. Things like that. I mean, they wanted to optimize the production of this incredibly important resource, and so they put all this government money into this program to try to really understand what was going on. And it turned out that the universe was much stranger than they had imagined. They thought it was just going to be a vanilla engineering effort, but it was not. Mm-hmm. And I think, even now, the things that we see now in terms of deep learning, this is research that we did 20 years ago. The neural network stuff, and that's we did it, all of a sudden it's back. But that was not the core research was done many years ago, and the industry has come in and taken over and really driven it forward. Now I would say that the kind of research going on in AI, the stuff going on in industry is light years ahead of what's going on in academics. You don't see the things coming out of Google, Microsoft Research, Facebook. It's just I think that they're making their resources available, so they want students to know what they want to continue to fund it, but it's become more like Bell Labs used to be.
How's that?
Bell Labs, you guys are so young. Bell Labs is that's where Unix was invented. Was in Bell Labs. Bell Labs was famous for being one of the greatest R&D centers in the world. There's always been a long history of places like IBM and AT&T Bell Labs having these fantastic research centers.
Mm-hmm. One of the things that's changed since the times of Bell Labs is that the expenses of conducting scientific research have changed. And I'm guessing that one of the big expenses to engaging in data science as a business is compute costs. They might not be very large, but I'm wondering...
we talk about like Enrico Fermi.
Yeah.
I don't know if I mentioned it. Enrico Fermi he had this thing, he called it the back of the envelope calculation. And the guy he was able to take any problem you needed to solve, take down a sheet of paper, which was about the size of an envelope, and just and just figure out the solution. Mm-hmm. He was and they say when he retired and they went to his office, they just found stacks and stacks and stacks of old envelopes where he would just, basically the old envelopes they would use to mail various things around the institute, and he would just solve problems on them. He had stacks of them, where he just solved thousands of problems. And a good scientist is able to look at a problem and come up and craft a quick and dirty solution, just right there. And that's the key to being able to do scientific work, is the fast turnaround time. You have to be able to solve problems and get fast turnaround times. You're not there to spend 6, 7, 8, 9 months building infrastructure. You're there to design good solutions and get them tested and to design good experiments. Part of the problem that a lot of companies have, and a lot of scientists have the same thing. We say this in theory, an experimentalist builds a device and then they just start measuring things. They have no idea what they're measuring. What are we measuring? Well, you can't afford to do that in business. You can't afford to just run random marketing experiments and see what happens. You have to carefully think about the design of your experiment so that when you see the result, you understand how much revenue did you generate, and can you figure out why you generated this much revenue.
So a lot of these actual implemented solutions that result from doing data science research in a business are oftentimes implemented and are running on servers somewhere. Like they're running somewhere in the cloud, they're outputting some results, and they're getting emailed to somebody on the business side who make some decision based on the output of those results. But one of the really interesting directions I think is a newer trend is that model, the whatever is being ran in the cloud is now being ran on device. Like there's recent news about Google partnering with hardware companies, or maybe vice versa, to get optimized TensorFlow processors.
Well,
So I'm curious. Are there where are we going with the location of computing, whether it's in your hand or whether it's in the cloud?
I think it's. There was a very famous paper video that came out a few years ago called The Unreasonable Effectiveness of Data. Mm-hmm. And it was basically the top guys at Google saying, you really don't need sophisticated algorithms. If you have enough data, even the simplest algorithms will do.
Yeah.
And this turned out to be completely wrong. They missed it totally. It turned out that, and this led to the development of Hadoop. And the idea that you just can run these simple algorithms in Hadoop.
That misunderstanding is what led to
that's completely wrong. And anyone who'd worked in neural network theory 20 years ago understood, that's totally wrong. So the development of where you're going to put the calculation, things are getting it's things you can do really really good work on your laptop with an SSD, and you have a GPU accelerator. I don't think it's a barrier. I don't think the calculations are as much of a barrier as it is the pipelines and the infrastructure and doing the wrong things. Mm-hmm. I think a lot of the calculation is very simple. Mm-hmm. And it's just there's with the development of Google TensorFlow and the Google TPUs and NVIDIA, it's just the price is dropping to the floor.
Well, what are some of the examples of handheld data science? Like, I know there's some really trivial stuff when it comes to putting masks on people's faces that follows their faces, like on
you mean like on the phone and that kind of stuff?
Yeah. So, the other thing that is a promising future application for device-based machine learning is classifying images locally versus having to send the images over.
Well, there's a lot of research in trying to compress models. Yes. So a couple of years ago, model compression was a big idea that you could somehow build a model. You could somehow take an ensemble of 1,000 models and then retrain another smaller model, which could get the same results of that ensemble. It only took one model, mm-hmm. and this was called dark knowledge. Okay. And this, it's just basically. I have a theory about they're basically like doing a high temperature average of this, but you are, and that is what they're doing. They take a temperature average. It's not a theory. That's what they're doing.
Okay.
And it's just getting, the algorithms are getting better and better. You're pre-training. Running a classifier is not a big deal. It's the training of the classifier that takes time.
Yeah. Well,
and
running the classifier involves serializing and persisting a model you have trained and distributing it.
Right. So the smaller it is.
Yeah.
The ability to build models that are very, very compact that can do quick classification. Mm-hmm. I think that's sort of the key is, how do you, there's a lot of research in it, but there's also will be, advances in hardware.
Sure, yeah.
And
the average phone will improve.
Yeah, this thing is like a supercomputer, what I had in undergrad. This is incredible what this thing can do. And it's just going to get faster and faster. Mm-hmm. So I think it's it's a Moore's Law type. People thought that, there aren't going to be any more advances in chip design or anything like that. And we're doing, and in fact, very, very, a lot of it are the special purpose chips you need. You have the data science requires having data flow architectures in hardware so that data can flow into the chip, a calculation can be run, and data flows out. That's not how existing things like the x86 work. They're designed for running multitasking operating systems. They're not designed to pipe data through the hardware. When we were in graduate school and I was running quantum chemistry, we had special purpose drivers and hardware that would pump data into the RISC processor so that we could run matrix multiplies. And they were very, very high performance. And that technology now, the stuff that was multi-million-dollar machines are now, commoditized, completely commoditized.
Pockets, yeah.
I think it's pretty amazing. Hot dog, not hot dog. Is that the...
Yeah, Silicon Valley, yeah.
Right, but I mean, but I also think because of latency effects, I mean, the latency is so low, you can afford to send the image over the wire and get a classification.
It kind of changes if you are live streaming video, maybe, where the bandwidth is meaningful. We're still in an early age enough where I think that is still a real issue.
Well, yeah, there's a lot of room for growth.
Oh yeah. So in the area of growth, I know we've kind of touched on this, but the capital costs of doing original data science are time, people time, compute time, and I guess what are the upper bounds on what are the forceful upper bounds on those?
I think a lot of the problems come up because people try to go too fast.
How's that?
Well, they think that, like, one of the problems people think that, well, what is data science? Well, we're gonna just do feature engineering. We're gonna run a logistic regression, and all we have to do is figure out what the features are.
Okay.
So we're gonna set up the regression. We're gonna hire 5 guys all out of school and some gals, and they're just gonna figure out all the features and just keep trying over and over and over. You just keep banging your head against the wall to try to make this thing work. And like, maybe that wasn't the right thing to do. Business does require thinking. You have to spend some time, and that's what makes it hard. Is that it's a different kind of thinking. You're trying to figure out how to frame the problem correctly, so that you understand where your biases are, and you understand if there's information leaking into the system. Mm-hmm. And that's the real challenge. It's not so much the engineering side of data science. It's not so much the experimental side of how do we trial. But so I think people simplify things too much. They simplify it, and then they just get this idea into their head. Well, we're going to try to make this go really cost effectively by scaling it horizontally and having all these different people. And then you realize, well, you're not really framing the problem correctly at the beginning, and you need to spend time on that. That's just part of setting up a business. It's like coming up with a new recipe for your restaurant.
Sure.
If I'll give you an example.
Before you
go ahead.
Before you do, I wanted to ask really quickly. I think a lot of our audience may not know what feature engineering is. Like, in terms of the process of coming up with a machine learning model for a problem and trying to iterate and improve that model's output so it conforms to what you it conforms to accuracy or measures of accuracy. What is feature engineering?
Well, yeah, the point is that you have some data somewhere and you're trying to predict something. Like, you want to, example, you want to offer somebody free play in a video game, and you want to induce them to play more.
Yeah.
And so this is a standard marketing trick, right? Doctors used to do this many years ago. They would offer, pharmaceutical companies.
Sure.
They would offer free samples to doctors, and the doctors would, they would then start writing prescriptions to their patients because they get the particular free samples, and so they would write more prescriptions, and so that's a common problem. And so when you talk about feature engineering, it's this idea that you're trying to take the data that's in your database and transform it into a form that's suitable for the algorithm. The algorithms can't figure it, they don't necessarily know what the right, they can't look inside the database and figure out what column to use, what normalizations you use, how do you rescale the data. There's a lot of just very technical things that go into designing a machine learning system. They don't just automatically find patterns in data. You have to prep it.
So I know with your engagements with consultants, it's tricky to talk about specifics, but can you give an example of where coming up with a new feature or engineering a new feature for a model radically changed the outcome for an engagement you had? Like,
no, let me give you a really good example.
Sure.
So imagine you're trying to... I can think of a couple. I can think of ones where the features have a very classic one is that you add features into the model,
yeah,
and it screws up the model completely.
Okay,
and it's not clear why would that happen. Why is it? There's sort of this naive idea that I just keep stuffing data into the system, and it should get better and better and better. Mm-hmm. Well, no, it gets worse. It can get worse. Why? Well, here's an example. We have one where we have a client who's trying to measure traffic on the internet. Okay. And they want to know, why is there a traffic change? And so they put the titles, maybe you put the title of your web page in, or the title of into the traffic engine. And it turns out some of the titles you put in are for Mother's Day. Okay. And you had your traffic went down the day after, sometime during Mother's Day. And so it looks like a lot of your traffic went down because of Mother's Day. No, that was a holiday effect. That was there, but that effect has to be removed because it's not a long-term effect. That was a spurious effect. That wasn't what you were looking for.
Sure. And so, I mean, that's an example of removing a feature, or I guess that's accounting for a feature that improves the model's performance and accuracy. But I guess I could give you an example that I'm thinking of from a previous job I held, which was in the email marketing space.
Yes.
A lot of this stuff is marketing. We were trying to forecast who would open our emails.
Right.
Or who would mark our emails as spam, of course.
Right.
And one of the ironies or one of the realities of email sending is people open their emails in different...
on different devices.
On different devices, different email clients. So certain devices, it's easier to open emails. So one feature that we feature engineered was to take into account what device the emails were opened on, or do some kind of look back of what devices have.
And then you start sending more email to people who have those devices because
they're more engaged.
They're more engaged, and we're just is that a good or a bad thing?
Depends. I mean, it depends on what the feedback loop is for your model. I guess.
Right. It's the same when you have a doctor and you start asking, you start giving all these doctors more free drugs, so they prescribe it more. So you start giving them more and more, but you may not necessarily. There's a bias effect.
Yeah.
Because there's a feedback loop that's a bias. You're giving the doctors who prescribe more, you're giving them more free, but they may not necessarily be the ones that are really prescribing more. It's just it seems that way because the ones who would prescribe more are it's this causal idea. It's called counterfactual reasoning. Okay. What would have happened if you had not done this? Would the doctor still have prescribed the drug if you did not give them the free sample? Mm-hmm. And those are the ones you're trying to target, are the ones you want to prescribe. If they're going to prescribe the drug anyway, why you don't need to give them the free sample? How do you figure that out? How do you figure out that counterfactual? Yeah. That's a huge problem as soon as these things go into production. Yeah. And understanding how to do that causal problem, that's a massive. Look, it's the same if you go to a restaurant and you always have the same.
I have a similar example that is relevant to lots of people's lives, which is the Netflix homepage.
Okay.
Where you get recommended what to view. One of the things that Netflix has a really hard time controlling for is what position did you see the show in or the movie in. So the counterfactual is if it had been in position 1 or position 2 of the carousel on the homepage of Netflix,
would you still click it? Would you still watch
exactly. So
right. No, and
controlling for that stuff is hard.
It's very hard, and the problem is that, and this is well understood in economic science. There's the difference between guys who just do logistic regression machine learning and an economist. An economist, their whole field is based around counterfactuals. How do you know what drives something? The whole field of Bayesian inference for things like medical, trying to understand how treatments affect people. Mm-hmm. I mean, this whole problem that people who have money are more likely to take the drug because they can afford it, but they're also more likely to be able to go see the doctor. So there's this weird feedback, and you have to account for that. And these systems, if you don't do that properly, will tend to introduce a bias that can really bite you later. You just basically sort of what you see is that there's people have done nothing. They haven't put any machine learning into production yet. They put it in production. You see a boost in revenue, and then it flatlines and it starts to drop. And you see what's happening. It's because you never removed all the biases that you introduced because you're showing people the same thing over and over again.
Is there? I know you have partners in your consulting, and you've trained people before. Is there a way to accelerate people's learning about how biases creep into data modeling? Like, are there any stories that you tell people when you catch them making this mistake, or do you know what I mean by that?
It's when I work with it's a tough one. Let me give you an example of how things you can see.
Sure.
We had a client once who was running models in production, and we just, and they got this idea into their head they need to do experiments over and over and over. You constantly do experiments. And not untrue, not wrong, but you have to do the correct experiment. Otherwise, you just kind of you're just kind of spinning your wheels. And so one of the things that we did was, what would happen if we took the exact same model and we put it into production twice? And half of the traffic randomly went to this instance, and half went to this instance. And then you measure how much money you're making. You measure the return, the revenue. And you find out that they're slightly different. Of course, there's a finite size effect. So that's the limit of what you can predict. Sorry, I can't, right? I mean, there's a factor of square root 2 or something in there that you can kind of get a little better, but there's a limit to what you can do if you run that there's just randomness in the traffic that you can't account for.
Yeah.
And that is something that is not at all obvious. Mm-hmm. But that's a day one type of thing that you need to do, is ask.
Is that a domain knowledge thing? Like, I mean, I guess that's not a domain knowledge thing. But are there examples where you've maybe been working with somebody less experienced and you were able to identify bias faster than they did just because of...
well, you got to look for it.
Okay. What is...
Look.
Sure.
You got to understand. Look, what is a bias in machine learning algorithm? It means that your residuals are correlated with your variables.
Okay.
If you put a feature in and you have an error, you go back and see. Are the features correlated with my errors? If they are, then you got a problem. I mean, in other words, you have a systematic error, the feature is inducing the error, right? It's causing it. So that you look for that kind of stuff.
So originally we were talking about how to fund or finance science projects. And I know we were talking really briefly about licensing and how kind of previously, for example, BlackRock, they had no interest in licensing. So if not licensing...
Well, they didn't want to do it. I mean, they had to do it. They just didn't... if they could figure out a way not to do it, they wouldn't... It's just like every company. If you could figure out a way to use something, to not pay for something...
But for a long period of time, I guess BlackRock did use MATLAB licensing.
Well, I'm sure they still do.
Sure.
Just because they want to do something doesn't mean they get away from... it's... I think... there's a huge rise of open source. And... companies that are very effective, they're going to contribute to the open source, but it's just something you have to use because it's just so much better. But MATLAB is a great product. Don't get me wrong; it's the premier product that's used in finance for financial modeling. Is Python taking over? Well, I mean, we're starting to see now, like companies like Bloomberg, for example, are beginning to offer IPython notebooks. That will run on their internal systems, that kind of stuff.
Even incorporated in like news articles. I've seen news articles, maybe it was in Nature magazine, where they'll publish online a reproducible study or analysis in a Jupyter notebook, right?
Well, that's an interesting point of view. You talk to vendors, and there's this notion that somehow maybe comes from the MBA programs. Yeah. That you can just give a PowerPoint presentation and an executive summary, and that's enough to understand what's going on. He said, "Wait, where's your GitHub repo? What do you mean?" Well, you claim that you made this analysis. We had a client. I worked for a hedge fund, and we wanted to look at the client who was trying to sell us some data. Yeah. So, well, show me the GitHub repo where you did the analysis. Well, we would never show that to you. I go, why not? Why would you not have that? And then I think to a scientist. Of course, you have to be able to show your work, and I think that was just the culture is changing. Mm-hmm. As more and more scientists enter into these businesses, and somebody tries to convince them they've done something, the standard is going to be much higher. The bar is raised.
Can you reproduce it?
You reproduce the results? I need to be able to reproduce this. Otherwise, I don't believe it. I need to know every single detail of what happened to really be able to say that I know what this is. And that's a very, very different way of thinking than saying, well, I have like an executive summary, or I have an API. I don't need to know how the API works. Mm-hmm. Completely different way of thinking.
This has been freaking awesome.
Well, you like this is good for you? Okay.
Yeah.
All right, I'm glad. All right.
Thank you for joining us.
Hey, thanks for having me. It's always fun to come over here. It's warmer over here.
Yeah,
Berkeley's warmer than the city.
Is there any kind of shout out we can make to Calculation Consulting, your guys' website?
Yeah, the website's always good, calculationconsulting.com. We're always happy to help people. And,
we'll do this again soon.
It would be fun. All
awesome.
right.
Thanks,
All right.
Charles.